In this video, we are going to talk about the language for how we represent acid-base reactions or all reactions occurring using something called mechanistic arrows. These are going to show us how the electrons move and change and how we go from reactants to products. So on this slide, we are actually introducing that language of mechanistic arrows. Mechanistic arrows show the movement of electrons or lone pairs to show how reactants transform into products, how bonds break, and how bonds form. So how they work is we start mechanistic arrows at an electron-rich source, usually lone pairs or a bond. So what have we done here? We see we have water with oxygen and two lone pairs. Those lone pairs are electron-rich. So we've started this mechanistic arrow that I'm outlining. You notice it starts at an electron-rich source, the lone pair on oxygen. Okay. We ended at an electron poor site, or something that is partially positive, like this hydrogen or this proton. We end electrons at electron poor regions, such as here. Okay, and then we saw that this bond broke. So the next second arrow starts at that bond and ends at that chlorine, and the effect of that is that we gave that lone pair back to chlorine. So in both of these mechanistic arrows, we are showing movement of electrons. We're showing how this lone pair on oxygen forms a bond with this hydrogen, and that bond is shown here on the new hydronium species we formed. The lone pair that lives in this bond between the H and the Cl on the reactant side becomes a lone pair on the Cl. Both times it is representing movement of electrons. What mechanistic arrows do not do is show movement of atoms, even though it may look that way. Let me clarify. When we're looking at the reactants to the products, we might say, hey, this hydrogen lives here now. So we're just going to draw an arrow showing that that hydrogen moved to live up there. That is not what mechanistic arrows show. We wouldn't want to show the mechanistic arrow showing a atom moving. Atoms become bonded or unbonded to things because of the way that electrons are moving. So we're going to practice this quite a bit. So our first step when we're given a reaction such as this one is to draw out the full Lewis structures for each species. We need to understand the carbons, the hydrogens, the lone pairs, formal charges next to all of them. So I'm going to pause the video for a second. I want you to draw out full Lewis structures for both reactants and products here. Okay, so here we drew out all four species as full Lewis structures with lone pairs and formal charges. Okay. And now we need to identify electron-rich and electron-poor regions within both of the reactants on the reactant side. So recall that the left-hand side is our reactant side. So we need to identify partial positive, partial negative regions using our knowledge of electronegativity. So pause the video here and assign partial positive and partial negative to this species and this species. So now that I've done that, we can see that there are regions of partial positive and partial negative within both species. So how are we supposed to know where to start our mechanistic arrow? We saw on the first slide that we start our mechanistic arrow at electron-rich places and end them at electron-poor places. Well, we have both of those things within this molecule, or within both of these molecules. And so when we have products, it is helpful for us to identify which bond is being broken. Just like we did early on when we were trying to identify which species are acids and bases. So the first thing that pops out to me, this hydrogen isn't there anymore in the products. This was a lone pair on my nitrogen, and now it looks like the hydrogen is here. So that looks like that's definitely the bond that's broken here, and the bond that's formed over here on the product side. And so when we assign acids and bases here on this next slide, we know that if this is the bond that's broken and this is the bond that's formed, we would call this the acid. It is the proton donor. The bond is broken between the O and the hydrogen. The thing that used its lone pair to do that job is called the base. Over on the left or the right hand side, that proton was living on the acid. Now it's living over on this species, and we call that the conjugate acid. And the species that used to have this lone pair, but now has this species became this species basically. The acid becomes the conjugate base because it now has an extra lone pair here that was given back to it as a result of this bond breaking and these two electrons going to live with the oxygen. Okay, and so now on this next slide we can finally draw our mechanistic arrows because we know what bond was breaking and what lone pair is doing the bonding. So we want to start our mechanistic arrows at our electron-rich spot that is going to form a bond with the electron-poor spot. So there's my first mechanistic arrow. I started it at the lone pair on the nitrogen, our base, ended it on the electron, the positive region on the acid. And you can go for either of these hydrogens. I went for this one. You could also go for this one that I'm highlighting in green. They're identical hydrogens, so you would pick one of those and draw your mechanistic arrow in that way. Your next mechanistic arrow is going to show how the two electrons that are living in the bond between the O and the H go back to the oxygen. And so I'm going to show how those two lone pairs go back. Let's use some highlighting here. These two lone pairs become this lone pair on that species is called the conjugate base. What was the acid became the conjugate base, and it has the lone pair now. The species that was the base that accepted the proton, now that proton's living here, we call that the conjugate acid. So we're going to start our mechanistic arrows at our base species and end them at the proton that was being donated from the acid. And so here I've redrawn all of that work for us, showing our mechanistic arrows. Notice that we start here. Let's use highlighter, I'm sorry. We start here, we end it here. We started here, and we ended it here. Okay. So now your job as part of your pre-class is to describe in words where you began your mechanistic arrow and why you chose that spot, and then describe in words where you ended your mechanistic arrow and explain why you chose that spot. We are going to practice this a lot in class, but the idea is that the reasoning behind where you start and end should leverage your knowledge about things we've practiced in before. Effective nuclear charge, electronegativity, for example, attraction, lone pairs, and things about the nuclei. Those are the types of terms that you should be thinking about when we're thinking about drawing our mechanistic arrow. Where's the partial positive and where's the partial negative?